Okay, let's have a look at these two questions on moments then. So start with number 8. The diagram shows a woman using a lever to lift a heavy object. It's a uniform plank with a wooden pivot as shown. The plank is 3 meters long and weighs 200 newtons. This object weighs 1,200. So if we draw it first of all, okay, I put the pivot in, which is away from the centre. There's the unknown force F. There's the weight of the heavy object, which is 1,200 newtons. And so we've got that on. We've also got the weight of the thing. So the weight of the object, because it does tell us that the weight is 200 newtons. It's a uniform plank, which means we can assume the weight to act from the centre. Okay, so 200 newtons drawn here. There's also a reaction force. Remember that, oops, I didn't quite go through the pivot with that. The pivot is pushing up on the plank. And none of this is moving. Nothing, it's not tilting, tipping or rotating. But these forces are still having an effect. And for it to be balanced, then remember the two conditions? 1, anti-clockwise moments must be equal to the clockwise moments. And 2, there must be no resultant force. So the forces up must equal the forces down. Okay, so let's just enable that R. So we've got all the forces on. We need the distances. So that's 2.2 meters. And the whole plank is 3 meters long. So the weight must be 1.5 meters. Then if that's 2.2 and that's 1.5, this bit here must be 0.7. And then that bit there must be 0.8 meters. Okay, so we're good to go. We've got all the forces labelled, we've got all the distances on, and we know where a pivot is because it tells us it is a pivot in this question. So that's part A, that's your free body diagram drawn. Then for B, we need to calculate force F. And for C, we need to calculate this reaction force. Okay, so there's 2 things that we need. We need to take moments about the pivot and use the principle of moments. And then we need to look at the forces. So if we let's start by taking moments. All right. Taking moments about the pivot. That's what we say. We take moments about the pivot, and that's our pivot. So what have we got? First of all, what have we got anti-clockwise? So the anti-clockwise moments. Well, this force is going to have an anti-clockwise turning effect. And this force is going to have an anti-clockwise turning effect. So we have, what's the distance of F to the pivot? So we've got F times 2.2 plus, what's the distance from this force to the pivot? So we've got 200 times 0.7. All right, we can simplify this a little bit. 2.2 F plus, and that is 140. Okay, now let's look at what we've got clockwise. So if I get a different colour pen, and in a second. So clockwise moments, this force, the 1,200, so clockwise moments, we've got 1,200 times, and the distance from the line of action of the force, perpendicular distance, is 0.8. Okay, now we can work that out, and it is 960. Okay, so we've got the two moments that add up in the anti-clockwise direction and the one in the clockwise. Now, for the principle of moments to apply, that means that the anti-clockwise moments must be equal to the clockwise moments, or the resultant, or the sum of, oops, that's not very good. So these two must be equal for it to be balanced. So 2.2F plus 140 must be equal to 960. And now we've got an equation there with just one unknown. Let's take the 140 over to the other side. What do we need to do to get rid of that? We need to subtract 140. So 2.2F equals 820, and F equals 372 newtons. Okay. Good practice to underline your answers in an exam or a assessment of any sort, so that the teacher can pick out what you've got. For part C, what's the reaction force? So, of course, the reaction force didn't have any effect, any turning effect, because it's acting through the pivot. But it is a force. You could say, oh, well, let's take moments about a different point and pick a different pivot point, a theoretical pivot point. But the easiest thing to do now is to use the second condition for equilibrium. Which is that the total forces upwards must be equal to the total forces downwards. So that is R equals F plus 200 plus 1,200. And if we substitute in our number for F, 372, add 200, add 1,200, we get the solution for C, the resultant force. Okay, so that's that one. The other one was, where are we? Question 20. So this one here, question 20. The diagram shows a child's mobile which is supported by a thread of negligible weight. AB is a uniform horizontal rod. By taking moments about point S, show that the weight W is 0.12 newtons. Okay, so let's see, let's draw it again. We have the fish on the left, 0.12 newtons. We have the fish on the right, 0.06 newtons. We have a string here, and it says we don't need to worry about the weight of the string. What else have we got? So we've got some distances. We've got 0.12 meters here, and we've got from there to there is 0.18 meters. And we've got the weight acting downwards, so it's roughly halfway. And does it confirm that it's uniform? Yeah, so the weight acting downwards. The question says, let's call that W for the weight force. The question says, take moments about point S to show that the weight is 0.12 newtons. So basically this is saying, this is saying calculate the weight and prove that the answer is 0.12 newtons. Okay, so what are we doing? We're taking moments about point S. So this is a case where you've sort of picked a pivot point, right? You could, if you wanted to, you could pick this point here, because of course there is another force. It's not a reaction force, it's a tension, I suppose, in the string. Wouldn't matter if you called it R and labelled it R. But by taking moments about this point, it means that that force, that tension, has no turning effect because it's directly through the pivot. We could, if we wanted to, we could also choose to take moments about point W, about that point there, in which case the force W would have no turning effect. All right? So you draw your diagram, put your forces on, put your distances on, and then you pick your pivot, the point at which, about which you're going to take all your moments. All right? So if we do exactly the same, so anti-clockwise moments and your clockwise moments, so fish pen, clockwise moments, and we will equate those. All right, so on this side, anti-clockwise, so this is our pivot point, right? That force at that distance, all right? Anti-clockwise moments, 0.12 times 0.12. So let's work that out. And it is 0.0144. One too many significant figures there for the minute. I'll leave it though, all right? Then on the clockwise side, this force W will have a clockwise turning effect, and this force will have a clockwise turning effect, all right? So clockwise moments are, we need to do a bit more with the distances here, don't we? So if that is the weight and it's halfway along, that distance is going to be 0.15, because the length of the rod, the whole length of the rod is 0.30 meters. So that weight must act halfway, and if that's 0.15 and and the distance from the end to the string is 0.18, that must be 0.03. Okay, so let's go back to our clockwise moments. We've got W times 0.03 plus that force times, and the total distance from that force to the pivot is 0.18. Okay, so we've got 0.03 W plus 0. Working out that bracket. Okay, all right, so for the thing to be balanced, the anti-clockwise moments must be equal to the clockwise moments. So 0.0144 must be equal to 0.03 W plus 0.0108. Okay, now let's rearrange this. The numbers aren't quite as nice as you get in a lot of algebraic problems, but let's take the whole of that, do this bit by bit. Okay, I've just swapped the sides, all right? Now, I'll stick with this W term, but I want to get rid of that term. So I subtract that from both sides. Okay. Keep going. 0.0144. Take away 0.0108 equals 0.0036. And to find W, divide both sides by 0.03, which is 0.12 newtons. So that is W, the weight of the rod. It's a child's mobile. Look at the forces involved, right? That's the weight of the fish on one end. That end isn't as big. The weight of the rod itself is similar. Okay, so that's a sensible answer, isn't it? Okay. Now we've got a fish. So this is a bit of a wordy question, really, isn't it? A third fish of weight 0.30 newtons is suspended from the middle of the rod. The thread supporting the mobile is moved along the rod so that the rod remains horizontal. On which side of the centre of the rod is the thread now attached? So just think about what will happen now if there's more weight put on this side of the pivot. That's what they're talking about doing, adding more weight here. So what's going to happen is the clockwise moment, clockwise turning effect, is going to increase. Yeah, it's going to hang down like that. So what are we going to do to balance it up? Well, what we need to do is we need to move that thread further over, okay, in order to balance it. So we're going to move the thread to the right. It says on which side of the centre of the rod is the thread now attached. So now rather than it being left of, we're moving it to the right, but rather than it being left of centre, it's going to be further over to that side. So it's going to actually be right of centre. Okay.